Welcome to my Advanced Database Management System course. In this section, we discuss about ACID properties, atomicity, consistency, isolation, durability. Let's enjoy. ACID is an acronym that stands for atomicity, consistency, isolation, and durability. These four properties are the fundamental principles that ensure the reliability and consistency of database transactions. Here's a brief explanation of each of the ACID properties. Atomicity. Atomicity ensures that a transaction is treated as a single unit of work that either completes entirely or is rolled back entirely if an error occurs. In other words, either all the operations within a transaction are successfully completed and committed, or none of them are. Atomicity prevents partial updates or inconsistent data states resulting from transaction failures. Consistency. Consistency ensures that the database remains in a valid state before and after a transaction. In other words, transactions should preserve the integrity and correctness of the database schema and data constraints. Even though individual transactions may change the database state, the overall consistency of the data is maintained. For example, if a database enforces referential integrity constraints, every transaction must adhere to these constraints to ensure consistency. Isolation. Isolation ensures that the concurrent execution of multiple transactions does not interfere with each other. Each transaction should operate independently of other transactions and should not see the intermediate states of other concurrent transactions. Isolation prevents phenomena such as dirty reads, non-repeatable reads, and phantom reads, which can occur when transactions are not isolated from each other. Durability. Durability guarantees that once a transaction is committed, its changes are permanently saved and persisted, even in the event of system failures or crashes. The changes made by committed transactions are stored in non-volatile storage, for example, disk, and remain intact even if the system experiences power outages, hardware failures, or crashes. Durability ensures that committed transactions are not lost and can be recovered in case of failures. In summary, the ACID properties provide a set of guarantees that ensure the reliability, consistency, and durability of database transactions. Adhering to these principles helps maintain data integrity, prevent data corruption, and ensure that the database remains in a consistent and reliable state, even in the presence of failures or concurrent transactions. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about data integrity concepts, entity integrity, referential integrity, transaction integrity, data validation, auditing, and logging. Let's enjoy. Data integrity refers to the accuracy, consistency, and reliability of data stored in a database or information system. It ensures that data remains unchanged and trustworthy throughout its life cycle, from creation to deletion. Here are some key concepts related to data integrity. Entity integrity. Entity integrity ensures that each row or record in a database table uniquely identifies an entity and that no primary key attribute contains a null value. Primary keys enforce entity integrity by guaranteeing the uniqueness and non-nullity of key attributes, preventing duplicate or missing records. Referential integrity. Referential integrity ensures the consistency and validity of relationships between related tables in a database. Foreign key constraints enforce referential integrity by ensuring that values in a foreign key column, referencing table, match values in the corresponding primary key column, reference table, preventing orphaned or invalid references. Domain integrity. Domain integrity ensures that data values stored in database columns adhere to predefined data types, formats, ranges, and constraints. Data type constraints, check constraints, and domain constraints enforce domain integrity by restricting the range of acceptable values for attributes, ensuring data consistency and validity. Transaction integrity. Transaction integrity ensures the correctness and reliability of database transactions, ensuring that they maintain the ACID properties: atomicity, consistency, isolation, durability. ACID-compliant transactions maintain data consistency and integrity by ensuring that database changes are atomic, all or nothing, consistent, isolated from other transactions, and durable, persist even in the event of system failures. Constraint enforcement. Constraints are rules defined on database tables to enforce data integrity rules and prevent invalid or inconsistent data. Common constraints include primary key constraints, foreign key constraints, unique constraints, check constraints, and not null constraints. Constraints are enforced by the Database Management System, DBMS, during data manipulation operations. Example: inserts, updates, deletes, ensuring that only valid data modifications are allowed. Data validation. Data validation ensures that data entered into the database meets specified criteria for accuracy, completeness, and consistency. Validation techniques include input validation, format validation, range validation, and cross-field validation, which are performed at the application level or enforced by the DBMS through constraints. Auditing and logging. Auditing and logging mechanisms track changes to data and record metadata about data modifications, providing a trail of accountability and enabling data lineage and forensic analysis. Audit logs capture information such as who made the change, when the change occurred, and what data was modified, helping to maintain data integrity and compliance with regulatory requirements. Data integrity is essential for ensuring the reliability, accuracy, and trustworthiness of data in databases and information systems. By enforcing entity integrity, referential integrity, domain integrity, transaction integrity, and constraint enforcement mechanisms, organizations can maintain data consistency, prevent data corruption, and ensure the reliability of decision-making processes based on data analysis. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about data encryption, encryption methods, asymmetric encryption, public key encryption, hashing data at rest, encryption, data in transit encryption, transparent data encryption, key management. Let's enjoy. Data encryption is a fundamental aspect of database security that involves encoding data in such a way that it can only be accessed or decrypted by authorized users or systems. It helps protect sensitive information from unauthorized access, interception, and tampering. Here's an overview of data encryption in the context of database management systems, DBMS. 1. Encryption methods, symmetric encryption. In symmetric encryption, the same key is used for both encryption and decryption. It is typically faster and more efficient than asymmetric encryption, but requires secure key management practices. Asymmetric encryption. public key encryption. In asymmetric encryption, different keys are used for encryption and decryption. Public keys are used for encryption, while private keys are used for decryption. This method provides enhanced security, but is slower and more resource-intensive. Hashing. Hashing is a one-way encryption technique where data is transformed into a fixed-size hash value. Hash functions are irreversible, meaning that it is not possible to reverse engineer the original data from the hash value. Hashing is commonly used for storing passwords securely. 2. Data at rest encryption. Data at rest encryption involves encrypting data stored in databases where it is not actively being used or transmitted. This protects data from unauthorized access in the event of a security breach or physical theft of storage devices. DBMSs often provide built-in features or plugins for data at rest encryption. 3. Data in transit encryption. Data in transit encryption involves encrypting data as it is transmitted between clients and database servers, or between different components of a distributed database system. Secure communication protocols such as SSL, TLS, Secure Sockets Layer/Transport Layer Security are used to encrypt data in transit, preventing eavesdropping and interception. Transparent Data Encryption, TDE. Transparent data encryption is a feature provided by some DBMSs that automatically encrypts data as it is written to disk and decrypts it when read into memory. TDE operates at the storage layer, encrypting entire database files or disk volumes without requiring changes to application code or queries. Key management. Effective key management is crucial for ensuring the security of encrypted data. This involves generating, storing, and securely distributing encryption keys, as well as implementing policies and procedures for key rotation, backup, and revocation. 6. Database-level encryption. Some DBMSs offer database-level encryption features that allow users to encrypt entire databases or specific columns within tables. This provides granular control over which data is encrypted and helps minimize performance overhead. 7. Application-level encryption. In addition to database-level encryption, applications can implement encryption mechanisms to protect sensitive data before it is stored in the database. This approach provides an additional layer of security and allows applications to enforce business-specific encryption requirements. 8. Compliance and regulations. Data encryption is often required by industry regulations and compliance standards, such as GDPR, General Data Protection Regulation, HIPAA, Health Insurance Portability and Accountability Act. Implementing encryption helps organizations meet these requirements and avoid potential penalties or fines. Organizations can mitigate the risk of data breaches, safeguard sensitive information, and maintain compliance with regulatory requirements. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about concurrency control techniques, locking, two-phase locking, 2PL, timestamp ordering, optimistic concurrency control. Let's enjoy. Concurrency control techniques are methods used in database systems to manage concurrent access to shared resources, such as database tables and records, while maintaining data consistency and integrity. Here are some common concurrency control techniques. Locking. Locking is a fundamental technique used to control concurrent access to database resources. Transactions acquire locks on database objects, examples, tables, rows, to prevent other transactions from accessing or modifying them concurrently. Locks can be of different types, including shared locks, read locks, and exclusive locks, write locks. Locking ensures serializability by enforcing a strict order of access to shared resources. Two-phase locking, 2PL. Two-phase locking is a concurrency control protocol that ensures serializability by dividing a transaction's execution into two phases, an expanding phase and a shrinking phase. During the expanding phase, a transaction can acquire locks on database objects, but cannot release any locks. During the shrinking phase, a transaction can release locks, but cannot acquire any new locks. Two-phase locking prevents deadlock and ensures that transactions are serializable. Timestamp ordering. Timestamp ordering is a concurrency control technique based on timestamps assigned to transactions. Each transaction is assigned a unique timestamp indicating its start time. Transactions are ordered based on their timestamps, and conflicts between transactions are resolved according to their order. Transactions with earlier timestamps are given priority over transactions with later timestamps. Timestamp ordering ensures serializability and avoids deadlock. Optimistic Concurrency Control, OCC. Optimistic concurrency control is a concurrency control technique based on the assumption that conflicts between transactions are rare. In OCC, transactions proceed without acquiring locks on database objects. Instead, they perform read and write operations on database objects and check for conflicts at the end of the transaction. If conflicts are detected, the transaction is rolled back and restarted. OCC is suitable for environments with low contention and high read concurrency. Multi-version concurrency control, MVCC. Multi-version concurrency control is a concurrency control technique that allows multiple versions of a data item to coexist in the database. Each transaction sees a consistent snapshot of the database at the time it starts, regardless of concurrent modifications by other transactions. MVCC uses timestamps or version numbers to track the visibility of data versions and ensures isolation between transactions. MVCC is commonly US. Deadlock detection and prevention. Deadlock detection and prevention mechanisms identify and resolve deadlock situations where transactions are waiting indefinitely for resources held by other transactions. Techniques such as deadlock detection algorithms, timeout mechanisms, and deadlock prevention policies, e.g., ordering locks, are used to prevent or resolve deadlocks efficiently. Serializable Snapshot Isolation, SSI. Serializable Snapshot Isolation is a concurrency control technique that combines snapshot isolation with serializability guarantees. SSI ensures that transactions execute with snapshot isolation semantics while preserving serializability. SSI uses techniques such as transaction dependency tracking and validation to detect conflicts between transactions and ensure serializability. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to Advanced Database Management System. In this section, we discuss about column family stores. Apache Cassandra, key features of column family stores, benefits of column family stores, best practices for working with column family stores, future trends in column family stores. Let's enjoy. Definition of column family stores. Overview of wide column data models. Structure. Columns grouped into families within rows. Scalability and distributed architecture. Use cases. Big data, time series data, etc. Introduction to Apache Cassandra. Data model in Cassandra. Key spaces. Column families, columns. Features. Distributed architecture. High availability and fault tolerance. Linear scalability. Tunable consistency levels. Wide column data model, distributed architecture for scalability and fault tolerance, tunable consistency levels, support for large-scale, high-throughput data ingestion and retrieval, scalability to handle massive datasets, high availability with no single point of failure, flexible schema design, efficient for write-heavy workloads, comparison of wide column and relational data models, use cases where column family stores excel over relational databases, effective data modeling, strategies for wide column schemas, cluster configuration and optimization, monitoring and maintenance practices, disaster recovery and backup strategies. Advances in distributed systems technologies, integration with other big data processing frameworks, predictions for the future evolution of wide column databases. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about cloud-native databases, scalability, resilience, distributed architecture, automation and orchestration, containerization. Let's enjoy. Cloud-native databases are database systems specifically designed to operate in cloud computing environments. They leverage the principles of cloud-native architecture to provide scalability, resilience, and agility for modern cloud-based applications. Here are some key characteristics and considerations of cloud-native databases. Scalability. Cloud-native databases are built to scale horizontally to accommodate fluctuating workloads and growing data volumes. They leverage cloud infrastructure services, such as autoscaling and elastic resources, to dynamically adjust capacity based on demand. Resilience. Cloud-native databases prioritize fault tolerance and high availability to ensure continuous operation in the face of failures or disruptions. They often employ replication, data redundancy, and distributed architectures to maintain data integrity and resilience. Distributed architecture. Cloud-native databases are designed with distributed architectures that span multiple geographic regions or availability zones. This allows for data replication, disaster recovery, and load balancing across distributed infrastructure, enhancing performance and reliability. Automation and orchestration. Cloud-native databases leverage automation and orchestration tools, such as Kubernetes and Docker, to streamline deployment, management, and scaling operations. They support infrastructure as code principles, enabling infrastructure provisioning and configuration through code. Containerization. Cloud-native databases are often containerized to facilitate deployment and portability across different cloud environments. Containerization enables encapsulation of database components, simplifies deployment workflows, and enhances resource utilization. Microservices integration. Cloud-native databases seamlessly integrate with microservices architectures, allowing individual database services to be independently deployed, scaled, and managed. They support APIs and service meshes for communication between microservices and databases. Managed services. Cloud providers offer managed database services that are fully managed and operated by the cloud provider. These managed services handle tasks such as provisioning, configuration, backups, monitoring, and patching, allowing developers to focus on application development rather than database administration. Security and compliance. Cloud-native databases implement robust security features and compliance controls to protect data in transit and at rest. They offer encryption, access controls, auditing, and compliance certifications to meet regulatory requirements and industry standards. Data integration and interoperability. Cloud-native databases support seamless integration with other cloud services and data sources, enabling data integration, ETL, extract, transform, load, and analytics workflows. They provide APIs, connectors, and data pipelines for interoperability with various data sources and applications. Cost optimization. Cloud-native databases offer cost-effective pricing models, such as pay-as-you-go and consumption-based billing, to align costs with usage. They also provide cost management tools and optimization recommendations to help organizations optimize their database spend. In summary, cloud-native databases are designed to leverage the scalability, resilience, and agility of cloud computing environments. They provide distributed architectures, automation, containerization, and managed services to support modern cloud-native applications and workflows. By embracing cloud-native principles, organizations can build and operate database systems that are highly scalable, resilient, and cost-effective in the cloud. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database course. In this section, we discuss about cardinality and modality, key characteristics of relationships, types of relationships. Let's enjoy. Relationships in the context of entity relationship, modeling, and database design represent the associations or connections between entities. They describe how entities interact or relate to each other within the system being modeled. Relationships are a fundamental concept in relational databases as they help establish the structure and integrity of the database schema. Key characteristics of relationships. Association between entities. Relationships define the connections between entities, indicating how instances of one entity are related to instances of another entity. For example, in a bookstore database, there may be a relationship between the book entity and the author entity to represent the fact that books are authored by authors. Cardinality. Cardinality specifies the number of instances of one entity that can be associated with the number of instances of another entity through a relationship. It defines the minimum and maximum number of occurrences allowed in a relationship. Directionality. Relationships can be either unidirectional or bidirectional, depending on whether the association between entities is one-way or two-way. In unidirectional relationships, one entity is considered the parent or primary entity, while the other entity is the child or related entity. Types of relationships. One-to-one, one-to-one. In a one-to-one relationship, each instance of one entity is associated with exactly one instance of another entity, and vice versa. For example, a person may have only one passport, and a passport belongs to only one person. One-to-many, one-to-m. In a one-to-many relationship, each instance of one entity can be associated with multiple instances of another entity, but each instance of the other entity is associated with only one instance of the first entity. For example, a customer can place multiple orders, but each order is placed by only one customer. Many-to-one, m-to-one. In a many-to-one relationship, multiple instances of one entity can be associated with a single instance of another entity. For example, multiple students may enroll in the same course, but each course is taught by only one instructor. Many-to-many, mn. In a many-to-many relationship, multiple instances of one entity can be associated with multiple instances of another entity. For example, multiple students can enroll in multiple courses, and each course can have multiple students. Representation of relationships. Relationships are typically represented visually in an entity relationship diagram, ERD, using lines connecting the related entities. The lines are labeled with the cardinality and optional participation constraints to indicate the nature of the relationship. In summary, relationships play a critical role in database design by defining the associations between entities and establishing the structure of the database schema. They help ensure data integrity, support data retrieval operations, and facilitate understanding of the data model within the system. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about blockchain and decentralized databases, consensus mechanisms, immutability. Let's enjoy. Blockchain and decentralized databases are two distinct technologies that offer different approaches to data storage and management. While blockchain is a specific type of decentralized database, decentralized databases encompass a broader range of systems that distribute data across multiple nodes in a network. Here's an overview of each. Blockchain. Definition. Blockchain is a distributed ledger technology that enables the secure and immutable recording of transactions across a network of nodes. Transactions are grouped into blocks, which are linked together in a sequential chain using cryptographic hashes. Once added to the blockchain, transactions cannot be altered or deleted, providing a tamper-proof record of all transactions. Decentralization. Blockchain operates in a decentralized manner, with no central authority or single point of control. Each node in the network maintains a copy of the blockchain, and transactions are validated and agreed upon through a consensus mechanism, such as proof of work, POW, or proof of stake, POS. Use cases. Blockchain is commonly used for applications requiring trustless and transparent transactions, such as cryptocurrency, e.g., Bitcoin, Ethereum. Supply chain management, digital identity verification, and smart contracts. Decentralized databases. Definition. Decentralized databases are database systems that distribute data across multiple nodes in a network, allowing for decentralized storage and access. Unlike traditional centralized databases, where data is stored on a single server or a cluster of servers, decentralized databases store data on multiple nodes, often using peer-to-peer P2P networking protocols. Decentralization. Decentralized databases distribute data across multiple nodes, providing fault tolerance and resilience against single points of failure. Each node in the network stores a copy of the database and collaborates with other nodes to ensure data consistency and availability. Consensus mechanisms. Blockchain relies on specific consensus mechanisms, such as POW or POS, to validate and agree upon transactions. Decentralized databases may use various consensus mechanisms or data replication strategies, depending on the specific implementation and requirements. Comparison. Centralization. Blockchain is inherently decentralized, with no central authority or single point of control. Decentralized databases distribute data across multiple nodes, but may still have centralized components or governance structures. Immutability. Blockchain provides immutable data storage, where transactions cannot be altered or deleted once recorded. Decentralized databases may not offer the same level of immutability, depending on the consensus mechanism and data replication strategy used. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about big data technologies and databases, Hadoop, Apache Spark, MongoDB, HBase. Let's enjoy. Big data technologies and databases are specialized systems designed to store, process, and analyze large volumes of data, often characterized by the 3 V's: volume, velocity, and variety. These technologies enable organizations to extract valuable insights from massive datasets and make data-driven decisions. Here are some key big data technologies and databases. Hadoop. Apache Hadoop is an open-source framework for distributed storage and processing of big data across clusters of commodity hardware. It includes components such as Hadoop Distributed File System, HDFS, for storage, and MapReduce for parallel processing of data. Apache Spark. Apache Spark is a fast and general-purpose cluster computing system that provides in-memory processing capabilities for big data analytics. It offers support for batch processing, real-time stream processing, machine learning, and graph processing. NoSQL databases. NoSQL, not only SQL databases, are non-relational databases designed to handle large volumes of unstructured and semi-structured data. They provide horizontal scalability and flexibility for storing and querying diverse data types. Examples include MongoDB, a document-oriented database that stores data in flexible JSON-like documents. Cassandra, a distributed database designed for high availability and scalability, ideal for time series data and real-time analytics. HBase, a distributed, column-oriented database that runs on top of Hadoop and provides random access to large volumes of structured data. Columnar databases. Columnar databases store data in columns rather than rows, which allows for efficient querying and analytics, particularly for analytical workloads. Examples include Amazon Redshift, Google BigQuery, a serverless, highly scalable data warehouse that provides real-time analytics on large datasets using a columnar storage engine. Distributed file systems. Distributed file systems provide scalable and fault-tolerant storage for big data applications. Hadoop Distributed File System HDFS, a distributed file system designed to store large datasets reliably across clusters of commodity hardware. Amazon S3, Simple Storage Service, a scalable object storage service provided by Amazon Web Services (AWS) that offers high durability, availability, and scalability for storing large volumes of data. Streaming platforms. Streaming platforms enable real-time processing and analysis of data streams. They are used for applications such as real-time analytics, fraud detection, and monitoring. Examples include Apache Kafka, a distributed streaming platform that allows for the ingestion, processing, and storage of real-time data streams. Apache Flink, a stream processing framework that provides support for event-time processing, state management, and exactly once semantics. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about backup and recovery, backup strategy, test backup and recovery procedures, multiple backup locations, monitor backup processes, document backup and recovery procedures. Let's enjoy. Backup and recovery processes are essential components of database management, ensuring data availability, integrity, and continuity in the event of hardware failures, software errors, or security incidents. Here are some best practices for backup and recovery in database management. 1. Define a backup strategy. Develop a comprehensive backup strategy that includes backup schedules, retention policies, and backup types. For example, full, incremental, differential. Consider factors such as data volatility, recovery time objectives, RTO, and recovery point objectives, RPO, when designing the backup strategy. 2. Regularly backup data. Perform regular backups of the database to capture changes and updates since the last backup. Establish backup schedules based on the criticality of data, business requirements, and compliance obligations. Automate backup processes to ensure consistency and reliability. 3. Test backup and recovery procedures. Regularly test backup and recovery procedures to verify their effectiveness and reliability. Conduct disaster recovery drills and tabletop exercises to simulate real-world scenarios and evaluate the organization's readiness to respond to data loss incidents. 4. Use multiple backup locations. Store backup copies in multiple locations, including on-premises storage, off-site storage, and cloud storage, to minimize the risk of data loss due to hardware failures, natural disasters, or security breaches. Implement a geographically distributed backup strategy for added redundancy. 5. Implement encryption. Encrypt backup files and data during transmission and storage to protect them from unauthorized access and data breaches. Use encryption techniques such as transparent data encryption, TDE, or data at rest encryption to safeguard sensitive information. Monitor backup processes. Monitor backup processes and log files regularly to ensure that backups are completed successfully and without errors. Set up alerts and notifications for backup failures or issues that require immediate attention. Monitor backup storage utilization and capacity to avoid storage space constraints. Document backup and recovery procedures. Document backup and recovery procedures, including step-by-step instructions, recovery steps, contact information for support personnel, and escalation procedures. Maintain up-to-date documentation for reference during emergencies and staff training. Configure backup and recovery. Set up backup and recovery options to protect against data loss and ensure business continuity in the event of hardware failures, software errors, or security incidents. Configure backup schedules, retention policies, and storage locations. Optimize performance. Configure performance settings such as memory allocation, buffer pool size, cache size, and query optimization parameters to optimize database performance and ensure efficient use of system resources. 8. Establish data retention policies. Define data retention policies that specify how long backup copies should be retained based on regulatory requirements, business needs, and data lifecycle management. Implement automated data retention and deletion processes to enforce policy compliance. 9. Perform regular data integrity checks. Conduct regular data integrity checks and consistency validations on backup files to ensure that backups are not corrupted or compromised. Use checksums, hashes, or data validation tools to verify the integrity of backup copies. 10. Regularly update backup and recovery plans. Review and update backup and recovery plans periodically to reflect changes in business requirements, technology advancements, and regulatory compliance standards. Incorporate lessons learned from past incidents and audits to improve resilience and responsiveness. By following these best practices for backup and recovery, organizations can minimize the risk of data loss, maintain data availability and integrity, and ensure business continuity in the face of unexpected events or disasters. Additionally, regular monitoring, testing, and documentation of backup and recovery processes are essential for maintaining the effectiveness and reliability of the overall backup. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about authentication and authorization, multi-factor authentication, MFA, authentication tokens, role-based access control, RBAC, database auditing best practices. Let's enjoy. Authentication and authorization are critical components of database security, ensuring that only authorized users can access and manipulate data within a database system. Here's an overview of authentication and authorization in the context of database management systems, DBMS. 1. Authentication. Authentication is the process of verifying the identity of a user or entity attempting to access a database. It ensures that the user is who they claim to be before granting access to the database. Common methods of authentication include username and password. Users provide a username and password, which are verified against stored credentials in the database. Multi-factor authentication, MFA. Users are required to provide multiple forms of identification, such as a password and a one-time code sent to their mobile device. Authentication tokens. Users are issued tokens or keys, which are used to authenticate their identity. Integration with external authentication systems. DBMSs can integrate with external authentication systems, such as LDAP, Lightweight Directory Access Protocol, or OAuth, for centralized authentication. Authorization. Authorization is the process of determining what actions a user is allowed to perform within a database once their identity has been authenticated. It controls access to specific resources such as tables, views, stored procedures, and functions based on the user's permissions. Authorization can be defined at different levels. Database level specifies which users are allowed to connect to the database. Object level specifies which users have permissions to perform specific actions on database objects. For example, read, write, update, delete. Row level specifies which rows of data a user is allowed to access within a table, based on specific criteria, e.g., ownership, role-based access control. Column level specifies which columns of data within a table a user is allowed to access or modify. 3. Role-based access control, RBAC. RBAC is a common approach to authorization that assigns permissions to users based on their roles or groups within an organization. Users are assigned to roles, and roles are granted specific privileges on database objects. This simplifies access control management by grouping users with similar permissions together. 4. Database auditing. Database auditing is the process of monitoring and recording database activity, including authentication and authorization events. Audit logs capture information such as login attempts, access requests, and changes to permissions, which can be used for security monitoring, compliance, and forensic analysis. 5. Best practices. Implement strong password policies, including requirements for minimum length, complexity, and expiration. Use encryption to protect sensitive data, both in transit and at rest. Thanks for watching the Advanced Database Management System lesson. Hope you enjoy the lesson. To learn more about Database Management System, please check the next lesson. Never stop learning. Thanks once again to enjoy the lesson. Welcome to my Advanced Database Management System course. In this section, we discuss about auditing and compliance, types of auditing, common compliance regulations, and standards. Database security controls. Let's enjoy. Auditing and compliance are essential aspects of database management, ensuring that organizations adhere to regulatory requirements, industry standards, and internal policies. Auditing involves monitoring and recording database activities, while compliance involves ensuring that database operations comply with relevant laws, regulations, and standards. Here's an overview of auditing and compliance in database management. 1. Auditing. Auditing involves tracking and recording database activities, including user logins, access attempts, data modifications, and administrative actions. Audit logs capture details such as the time, date, user, and action performed, providing a comprehensive record of database operations. Compliance. Compliance refers to adherence to laws, regulations, standards, and internal policies governing data management, privacy, security, and transparency. Compliance requirements vary depending on the industry, geographic location, and nature of the organization's operations. Common compliance regulations and standards include General Data Protection Regulation, GDPR, protects the privacy and rights of individuals in the European Union, EU, by regulating the processing of personal data. Health Insurance Portability and Accountability Act, HIPAA, ensures the security and confidentiality of healthcare information and electronic health records, EHRs, in the United States. Compliance. Compliance refers to adherence to laws, regulations, standards, and internal policies governing data management, privacy, security, and transparency. Compliance requirements vary depending on the industry, geographic location, and nature of the organization's operations. Common compliance regulations and standards include General Data Protection Regulation, GDPR, protects the privacy and rights of individuals in the European Union, EU, by regulating the processing of personal data. Health Insurance Portability and Accountability Act, HIPAA, ensures the security and confidentiality of healthcare information and electronic health records, EHRs, in the United States. Payment Card Industry Data Security Standard, PCI DSS, sets security standards for organizations that handle credit card transactions to prevent data breaches and fraud. Sarbanes-Oxley Act, SOX, regulates financial reporting and disclosure requirements for public companies to prevent accounting fraud and protect investors. Compliance requirements often include data encryption, access controls, audit trail retention, data retention policies, data breach notification, and regular security assessments and audits. 3. Database security controls. To achieve compliance, organizations implement various database security controls, including access controls restrict access to databases, tables, and sensitive data based on user roles, permissions, and least privilege principles. Encryption. Encrypt data at rest and in transit to protect against unauthorized access and data breaches. Authentication and authorization. Implement strong authentication mechanisms and role-based access control, RBAC, to verify user identities and enforce access policies. Auditing and monitoring. Monitor database activities, generate audit logs, and conduct regular security audits to detect and respond to security incidents. Data masking and anonymization. Mask sensitive data to prevent unauthorized access and maintain privacy while preserving data utility for testing and development purposes. 4. Best practices. Establish a comprehensive security policy that outlines roles, responsibilities, and security controls for database management. Regularly assess and update security controls to address evolving threats and compliance requirements. Conduct employee training and awareness programs to educate staff about security best practices and compliance obligations. Implement a risk management framework to identify, assess, and mitigate database security risks effectively. Engage with legal counsel and compliance experts to ensure alignment with applicable laws, regulations, and standards.